Yeah, that's 3 examples for application layer protocol. Actually, there are a lot of more application layer protocols we didn't cover. That is only to give you some example to know a little bit about what the application layer do. Now let's begin the transport layer. So the transport layer actually provides the end-to-end transmission or end-to-end connection. They can receive the data from the application layer protocol. So in application layer, they want to send a message to the internet. Actually, they didn't send the message directly to the internet. Instead, they transmit the message to the transport layer. And then the transport layer will add some header and then send to the network layer and to lower until the internet. Okay, so transport layer will receive data from the application layer and encapsulate the data and then send down. And we call a packet in the transport layer to be segment. There are 2 typical transport layer protocol, TCP and UDP, which provide a reliable transfer protocol, and UDP provide a connectionless, unreliable protocol. These are the header format of TCP and UDP protocol. Because TCP provide a lot more functions, so actually here in the header of TCP, they include more domain. So for example, the common domain for TCP and UDP are the source port, the destination port. So the port number is very important for different application. Typically, they will use different port in the computer. Okay, so in both TCP and UDP header, we will have the source port, the destination port. And in UDP, they have a length. This is the length of the total packet and some checksum. That's all. Very easy. But for TCP, because we need to provide the reliable data transfer, so we need to give some ID or give the sequence number to every packet. And also we will add some window. This is used for flow control and congestion control and some other domains. So that is the header for TCP. Now let's look at some important concept one by one. So the first important concept is the port number. Just now we said that in the header of TCP protocol, you need to give the source port number and destination port number. So what is port number? Actually, we have said that different applications use different ports to transmit data. So for example, in your computer, you are running 2 applications. One is the web browser, another one is the remote login. Then the web browser will send the message through port 1024, and the telnet may send the message from the port 1231. So different applications use different ports to send message. So actually in the receiver end, it's very easy for it to transmit the corresponding message to the correct application according to the port. Okay, so that is port number. And for TCP connection, for the TCP, you need to know that to guarantee the reliable data transfer, actually TCP need to first set up a connection. So this is the sender, this is the receiver. For example, before sending any data, they need first to set up a connection, or you can think of that as an end-to-end link. Okay, so how to set up this connection? The idea is very easy. The sender sends a packet, meaning that I want to set up a connection. After receiving the message, the receiver sends back a message with its acknowledgement bit to be set. You say that, okay, I'm ready, you can set up, and you can begin with this sequence number. You can begin with A, and my message will begin with B, and then receive this message. The PC1 will send acknowledgement feedback to tell it that, okay, I got it. Now a connection is established. So we call this a three-way, 1, 2, 3, three-way handshake. After this handshake, these two PC has agreed on this connection. Also, in TCP protocols, to guarantee that the packet are transmitted in sequence to the destination, they need to give the number, the sequence number, to each packet. Actually, the sender numbers each byte of the byte which should be transmitted to the receiver of the TCP. For example, in this packet, the first byte is A plus 1, the next byte is A plus 2, and the third one is A plus 3. Then the PC1 will give a sequence number of the first byte as the sequence number of this packet. So the sequence number of this packet should be A plus 1, and then they send this packet into the receiver. The first byte number is A plus 13, so in this packet, the sequence number should be A plus 13, which is also the number of the first byte. Because the intermittent transmission actually may not be reliable, so in the receiver part, when they receive the packets, maybe it is out of order. So by checking the sequence number, they can know that, okay, I receive 1, 2, 3, 5. Then 5 is out of order, so I will ask for the packet 4 once again. And until packet 4 comes, I can send the 5, 6, 7 to the upper layer. So in that case, the transmission can be in sequence. Look at the detailed number in sequence and ACK to understand the operation of TCP. So here, the number in sequence means the starting byte in this packet. And if you look at this from 1 to 2 data transmission, you need to look at the sequence number of PC1 and the ACK number of PC2. So the ACK of PC2 means that I have correctly received the byte from A plus 1 to the byte A plus 12. So the next expected byte is A plus 1 plus 12. So the number in the ACK means that I have correctly received the previous byte, and the next byte is I expected is written here. Okay, so the PC1, after receiving this message, they can know that, okay, you have received all the byte before this number. Then I can send the byte from this number to you. Okay, and because the length is 66, if the receiver received this packet correctly,
then it will tell the PC1 that the next byte I'm expecting is A plus 13 plus 66.
So there's one question. If I look at this direction data transmission from 2 to 1, then how shall we analyze? Yes, we should analyze this sequence number and this ACK. So here, one question is that why the ACK number here is B plus 1 and the ACK number here is still B plus 1? Yes, you may notice that is because in this packet, that is a pure acknowledgement packet. They have no payload. Here the payload is 0. So the PC1 didn't receive more byte after this message. So the next byte they are expecting is still B plus 1. So it's not changed. Okay. Okay. The TCP actually uses the sliding window mechanism to control the data transmission rate. So, for example, during the three-way handshaking, the receiver will first check the empty buffer size. For example, here, the receiver has 3 empty buffer size, which means that it can receive at most 3 bytes. So they will write 3 into the window field and notify the sender that, okay, the maximum number of bytes you can send is 3. And then at the data transmission stage, the sender can send at most 3 bytes. And then in the receiver, it will put each byte into the buffer and waiting for the upper layer to obtain the byte. Here, for example, all the buffer is full, and then here the upper layer has already obtained 1 byte out. Then there are 1 empty byte. So the receiver can tell the sender that, okay, now my window size has changed to 1. At most, you can send 1 byte here. So this is the mechanism of window sliding. It enables the receiver to control the sending rate of the sender. So here is one question. Why does the window field of the segment sent by the PC1 remains unchanged? So you see that the window field sent by the PC1, here is 3, here is 3, and here, all of them are 3. Why? Why it is remain unchanged? Okay, think of that. Yeah, that is because from the receiver, from the PC1 point of view, first they have 3 bytes empty buffer size. And during all the stage, the PC2 sent no packet, no byte to PC1. So from PC1's point of view, the buffer is still empty. The buffer size is still 3 without changing. So the window field they notified PC2 remains unchanged, remains 3. After the data transmission, finally, the TCP connection should be shut down to release the resource allocated to this connection. And for shutdown, typically they use the 4-way handshake. It's a little bit complicated than the connection established. In the established, we are 3-way handshaking, right? So for the shutdown, actually, this sender, if the transmission from 1 to 2 is finished, then this PC1 can try to finish this connection. They first send a packet with the fin domain set to be 1. And then the PC2, after receive this fin packet, they will send an ACK packet. After receiving this ACK packet, PC1 will not transmit any data later on. And to close the data transmission from 2 to 1, actually the PC2 needs to send a message, which is the fin message. And then the PC1 send back the feedback, the fin ACK message. So using this fin message and fin ACK message, the transmission from 2 to 1 can be closed. So until these 2 connections data transmission are both finished, the TCP connection can be shut down. Okay, and why this message cannot be integrated into one message? That is because after this directions transmission finish, actually the PC2 may still have some data need to be transmitted back. So the PC2 need to wait until all the all the data in this direction finished transmission. They can send the fin message out. So we need at least 4 messages for TCP shutdown.